So we've been covering a lot of different factors. One of the things I want to talk about now are z-scores and how z-scores are used to get to our first inferential statistics. So we've already been using z-scores, though kind of in the background in our correlations and regressions that we've been discussing. Again, they're just looking for patterns of behavior. And one of the things that you'll note about correlations and regressions is they are not related to the actual scale of measurement. In other words, if you have one DV that's on a 0 to 5 scale and an IV that's on a 10 to 50 scale, if you have something that's 0 to 100, you can compare it to 1 to 5. The values of the variables are not related to the outcome. The outcome is on a -1 to +1 scale for correlation at least, and that is based on the strength of the correlation and what direction it is. One of the things that allows this to happen in the background is z-score computations. And what a z-score basically is it's the process that we use to make it to where we aren't concerned with the original scale. In other words, it's a conversion to where we can convert a single measure that is on any particular scale, 0 to 3, 10 to 20, 100 to 1,000, and put it into what we call standard deviation units or Z units. So that's really what we're talking about here with z-scores. And though z-scores have been a part of what's been occurring currently, when we start talking about inferential statistics, in other words, statistics that are going to be used not just for quasi-experimental designs, but also experimental designs, where we're looking for specific differences between groups, for instance, the z-score or the z-test is going to be one of the very first ones we talk about. So again, what do we use z-scores for? We use them to compare scores. So for example, we have Bill and Jake have Dr. Meeks for Psych 220 class and took the same exam. Bill scored a 92 and Jake scored an 85. Who did better on the exam? So we can definitely say that within this, we know that Bill and Jake took the same test in the same class with the same instructor on the same date. And therefore, it's pretty easy to say that Bill did score higher than Jake, 92 versus 85. And likewise, example 2, Kyla has Dr. Nadler for 220, so she's taking it with someone else, and scores an 84. Now, this is a different class. Now, it's the same class number, but it may be a different test. It may be from a different date, and it's definitely with a different instructor. So if we just looked at the base scores, knowing that it was on a 0 to 100 scale, the test, we would probably say, well, I guess Kayla did worse than Jake or Bill. And objectively, she did. Everyone's on the same scale. However, if we ask the question, how does Kayla's score compare to Bob and Jake's, we need more information. We need to know what the actual distributions of those two tests were, how difficult they were. For example, maybe Dr. Meeks is a better instructor than Dr. Nadler, or vice versa. Maybe one of them had a harder test. Maybe one of them tested at a different time where there was different constraints on people's performance. So if we're looking for just objectively on a 1 to 100 scale, ignoring the individual differences of class, instructor, and time, we can basically say Bill scored highest, Jake next, and Kayla last. However, if the question again is a comparative, we need to go further. And that becomes how rare is each score in the distribution. So another example, Bill's score on the Rosenberg self-esteem scale is 25. Larger numbers reflect higher self-esteem, and the largest possible score is 30. Jake scored on the Janus field social adequacy scale was 100. Larger numbers reflect higher self-esteem, and the largest possible score is 115. Who has the higher self-esteem? Now this gives you a better example of something where we can recognize that there's a little bit of a difference here. Both measures measure self-esteem. Both measures, we assume, have been highly validated and constructed very rigorously. But one of them is on a 1 to 30 scale, and the other one is on a 1 to 115 scale. So how does Bill's 25 compare to Jake's 100 on these two different tests? So again, we have to ask, how rare is each score within that distribution? Final example, Lydia's IQ score is 90. Large scales reflect higher IQ. Largest possible scale on this particular score is 200, and these are basically 0 to 200 scale. Lydia's GPA is 1.67. Largest possible GPA is 4, so this is on a 1 to 4 scale. Did Lydia do as well on the IQ test as she does in her classes? In other words, how do these two scores measuring different constructs compare to each other, though they are somewhat interrelated? So an IQ of 90 on a 200 scale versus a GPA of 1.6 on a 4-point scale. So again, our question is, how rare is each score? So what is a Z or standardized score and what's it good for? Z-scores allow you to compare across these examples. It allows you to compare scores from different samples in the same test. It allows you to compare scores on different measurement scales, and it even allows you to compare scores on different measures. So again, people taking the same test or a very similar test in two different situations, people taking different measures of the same construct, or potentially people even measuring on two different constructs. So our first example again was test scores, both on a 0 to 100 in two different classes. The second example was looking at self-esteem from two different measurement scales. And the final one was looking at actual IQ and GPA, two different kind of measures. So Z-scores convert whatever the original measurement is, whether it's on a 0 to 100, whether it's on a 0 to 200, whether it's on a 1 to 4-point scale, to standard deviation in mean units. Therefore, 0 is the midpoint of the scale and represents the mean score of the original distribution. So basically, if you have a Z of 0, you know that person, whatever that measurement was, that they performed dead center of the normal distribution. In other words, half the people were above them, half the people were below them. Sign indicates whether the score is above or below. So if you have a negative Z-score, it means that you are scoring in the lower half of the distribution. If you have a positive Z-score, you're in the upper half. And the number indicates how much the score differs from the mean in standard deviation units. So basically, a Z-score of 1 means that you are 1 standard deviation above the mean in your score. And if you had a Z-score of -1, you'd be -1 standard deviation unit from the mean or the average. Therefore, we can use to determine the probability of the score occurring to test hypotheses and to compare scores across these three situations. So again, Z-scores are based on some assumptions, and one of those assumptions is that you have a normal distribution. And a normal distribution does not have to be perfect, but basically there are statistical tests, and we can talk about those later in the class, to find out is a distribution close enough. But a true standard deviation or a true standard or distribution score is going to look like this, that the mean is going to represent the actual average, and as you move away from the mean, scores become less and less common. And generally speaking, when we talk about standard deviation units, one standard deviation unit above and below the mean is going to capture about 68 to 69% of the total of population. So 2/3 of people are going to be within one standard deviation on a normal distribution. As we move to 2 standard deviation units, we start to get to a smaller or larger number. So for example, if you're 2 standard deviation units above the mean, at this point, we're actually looking at you being probably in the 96th to 97th percentile. In other words, you scored higher than 96 or 97%. Likewise, if you're 2 standard deviations below the mean, you're again 97 approximately percent of people scored above you. And as you go to 3 standard deviation units, we're usually looking at less than 1% of the population hits this area. So basically, if you have a Z-score of 3, you are probably one of the top scores that ever occurred within that distribution. Likewise, if you had a Z-score of -3, you're at the very bottom of that distribution. So when we're looking at Z-scores, all we need to do is, no matter what, when we calculate the mean, it's an actual value. So if I'm on a 0 to 10 scale and I get a mean of 7, that mean is representing the center of the distribution, but it is dependent on the 1 to 10 scale. And I would calculate my standard deviation. In this case, it might be 1.72. So 1.72 above 7 and 1.72 below 7 would be that 68% of the population. However, that's again dependent on my scale, in this case 0 to 10. What I want to be able to do is convert it to a Z-score to where the mean is always 0 and the standard deviations are always 1. So that is the purpose of calculating the Z-score. So again, my mean is always going to be 0, and 2 units is going to represent 2 standard deviation units regardless of the scale. So what is a z-score or standardized score and what it's a good for? Independent of the original measurement scale and sample size. So we don't get information about how big the sample was. We don't get the actual standard deviation and mean. We use the standard deviation and mean and the sample size to calculate the z-score. And we create a standardized scale that reflects the number of standard deviation units above or below the mean of someone's score. Because the standard deviation itself is adjusted for sample size, remember that when we calculate standard deviation, the bottom of the equation is n-1, and z is based on that standard deviation, the z is automatically adjusted for the sample size. So z is someone's individual score minus the mean divided by the standard deviation. That gives us our z-score. So if we know, for example, that someone had a 90 on a test, the mean was an 80, and the standard deviation was a 5, we would take 90 minus 80, so we'd have positive 10, divided by the standard deviation of 5, we'd have a z-score of 2. They were 2 standard deviation units above the mean. So let's go through some quick examples here and just walk through this math. So again, we have Lydia's IQ at 90. We know that the IQ test has a mean of 100 and a standard deviation of 15. By the way, most measures of cognitive ability, IQ tests, are set up on this scale, where the mean is actually adjusted to be 100 and the standard deviation has been adjusted to be 15. So taking that, we can quickly calculate Lydia's z-score. 90 minus 100 is negative 10, divided by 15 is negative 0.67. So Lydia's z-score on her IQ is negative 0.67. So she's in the bottom of the IQ score, but there are people that definitely scored worse than her. Her GPA, remember, now again, in this case, GPA can vary from university to university, class to class, but we actually get the GPA average for this university, and it turns out to be 2.0 with a standard deviation of 0.5. Lydia's GPA was 1.67, and again, we can use this information to calculate. So again, we're using that same equation, and 1.67 minus 2 becomes negative 0.33, divided by 0.5 becomes negative 0.66. So again, we can see that actually Lydia's IQ and Lydia's GPA are about where we expect them to be. They are basically at the same level. One is negative 0.67 z-scores from the mean, and the other one's negative 0.66 z-scores from the mean. And again, if we graph that out, we would see a very similar spread. So again, z-scores at their basic level can be used to determine the probability of a score occurring and compare a score from one distribution or score from another. And that's primarily what we're going to be using z-scores for initially, is that initial computation, the person's score minus the mean divided by the standard deviation. Now, in order to do that, we have to have the mean and standard deviation of the population or the sample that we're using to be able to calculate someone's z-score. But this simple equation allows us to basically go back to any of the examples we used earlier to calculate z-scores.